Hello again. This is Math 1120 coming to you from the College of DuPage. The title of this lecture is Interference, Beat Frequencies, and the Doppler Effect. And as always, please be an active listener when watching this video. By way of introduction, previously we talked about interference effects that occur when two different waves with the same frequency overlap in the same region of space. Now we're going to look at the superposition of two waves with equal amplitudes but slightly different frequencies. This phenomenon occurs, for example, when two guitar strings with slightly different frequencies are sounded together, or when two organ pipes that are supposed to sound exactly the same pitch are slightly out of tune. What you hear from two sound waves with slightly different frequencies is a slow pulsing or beating called beats. So here we have a graphic of two sound waves, a blue one and a red one, with slightly different frequencies. And what happens is they will catch up with one another as they go along because the velocities of the waves will be different. And so sometimes they will be in step with each other and they will add, and other times they'll be out of step with each other and they will subtract. Now, when you add this together as vectors, the two waves interfere constructively when they are in step and destructively when they are a half cycle out of step. So the resultant wave waxes and wanes in intensity, forming beats. So you see there's a beat and there is another beat. So we're basically showing two beats in time for these two waves. Now when the two waves with different frequencies interfere, it fluctuates in amplitude, the resultant wave, and we hear these fluctuations as beats. And so you can see what's happening here. Now the resulting wave looks like a single sine wave with varying amplitudes that goes from a maximum to zero and back again, and you see it going up and down. In this example, the amplitude goes through two maxima and two minima in 1 second. Thus, the frequency of this amplitude variation is 2 Hertz. The resulting variations in amplitude are beats. And the frequency with which the amplitude varies is called the beat frequency. So in this example, the beat frequency is the difference between the two frequencies. If the beat frequency is a few hertz, like it normally is in ultrasound, we hear it as a waver or a pulsation in the tone. And in another video, I let you listen to this. Now we can show, and I'm going to do that right now, that the beat frequency is always the difference between the two frequencies. And one of them is F1 and the other one is F2. Now, since they are, and we're just going to start with this, we're going to say, suppose the corresponding periods, which is related to the frequencies, are T1 and T2, and T1 is less than T2. So suppose the two waves start out in step at time t equals 0. They will be in step again at the period of the beat. And that means that the first wave has gone through exactly one more cycle than the second one. So we let n be the number of cycles of the first wave, and so we have this. The period of the beat is n times t1, and the period of the beat is also n minus 1 times t2. So you see this is two equations and two unknowns, and we can solve for n and substitute in, and we get that this is the period of the beat in terms of T1 and T2. Now, the period of the beat is just the period of the beat. Its reciprocal is a beat frequency. So the frequency is 1 over the period of the beat. So you see it's 1 over this. I'm basically just turning this upside down. But this is the same thing as the difference between these two fractions. So that means the beat frequency is the difference between the two frequencies. Turns out this is an important equation that we'll use to solve Doppler effect problems. Now this does exist in nature because barn owls locate their prey by making use of the fact that each ear receives sounds of slightly different times, because if they're not pointing directly at their prey, it'll go to one ear faster than the other. And this small difference is processed by the brain, and the owl swivels its head until they reach the ears at exactly the same time. At that null point, the head and eyes are facing directly towards the sound source. That's where the prey is. Owls are capable of detecting time differences in the sound waves received by the ears as small as 10 microseconds. Nature is really amazing. Also, sonar, which was a precursor of ultrasound, was used to find a ship called the Portland, and they were searching for it, and it sank. And so you see the water is way up here where you're looking at this, but they're sending ultrasounds down and it's bouncing back. So what you can see here, and what they were doing in this application, the frequency of the sound transmitted was about 50 kilohertz, much less frequency than what you're using with your ultrasound. And that is well above the upper limit of the human ear, which is about 20 kilohertz. So when the sound waves reach the object, they're reflected in various ways, depending on the position and so on and so forth. But these differences allowed them to come up with this image. So you can see two smokestacks, for example, in this triangular region here that's also is providing power to the ship's side paddle wheels. Now we're going to turn our attention to the Doppler effect. You probably noticed that when an ambulance approaches you with its sirens on and you're standing still, the pitch seems to drop as the vehicle passes. This phenomenon is called the Doppler effect. When a source of sound and a listener are in motion relative to each other, the frequency of the sound heard by the listener is not the same as the source frequency. We can work out a relationship between the frequency shift and the velocities of the source and the listener. That's going to be the Doppler effect. So let's start with the situation of a moving listener. So you see, here's the policeman who is listening, and here is somebody standing stationary, but they're playing a boombox, and so this is sending out sound. So this is a moving listener. Okay. So the source emits a sound wave with frequency f sub s, frequency of the source, and a wavelength, which we know from our wavelength equation is lambda equals the velocity of sound divided by the frequency of the sound. This is one of our fundamental equations. Lambda is equal to v over f. So we saw the figure, and we can see what's happening here. And the figure shows several waves with crests separated by equal distances, and these distances are, in fact, the wavelength. So the waves approaching the moving listener have a speed of propagation of v plus vl, because this speed adds with the speed of sound relative to the listener. So the frequency f sub l that the listener hears with the wave crests arrive at the listener's position at a greater frequency. So it is v plus the speed of sounds plus the velocity of the listener divided by lambda. And we can use the fact that lambda is equal to v over the frequency of the source, and we can simplify that, and we end up with this equation. So you see the frequency of the listener is this multiple of the frequency of the source. So as the listener moves towards the source, that means that this velocity is bigger than 0. Here's a sound of higher frequency. than the stationary listener hears. If a listener is moving away from the source, that means VL is going to be less than 0. It hears a sound that is lower than the frequency, and that is called a lower pitch. We can also think about if there's a moving source. Now here you have the police officer is here, and the police officer also can be moving or not. But now we have the source is moving, so there's a V sub S. So now suppose a source is also moving with V sub F. The wave speed relative to the air is still unchanged. It's a property of the wave medium. It is not changed by the motion of the source. In this case, the wave medium is the air. But the wavelength is no longer equal to V over F of source, and here's why. The time for the emission of one cycle of the wave is the period, t equal 1 over F sub s. But during this time, the wave travels a distance of V times t, capital T, equal V over Fs, and the displacement then is Vs, t, is equal to Vs over the frequency of s, and it could be positive or negative. So the wavelength is the distance between successive crests and is determined by the relative displacement of the two. And as this figure shows, this is the difference between the front of and behind the source. See, these are getting shorter here, these are longer here. So lambda then, in the region to the right of the source, lambda is equal to this lambda minus that lambda, which is this expression. And that is to the right of the source. To the left of the source, the wavelength is this. Here they are subtracting, here they are adding. So when the velocity of the source is positive, as it shows here, the waves are compressed in front and stretched out behind, as you can see. Now, if we want to find the frequency heard by the listener, which is this policeman, we can substitute equation 1218, and this is equation 1218, into the first form of equation 1216, and 1216 is shown up here. So we substitute, you should check this algebra out. And then we solve for the frequency of the listener, and we get the frequency of the listener is this. And when we do the substitution, we get this, which we can rewrite as, and this is the equation we have when both are moving. So this is called the master Doppler effect equation. So for a listener L and a source S moving along a line joining them, and by the way, in ultrasound it's not always along a line, and you'll see that in the other video that I show you and in our classroom discussion, the frequency FL heard by the listener is related to the frequency Fs produced by this master equation. So FL is equal to V, the speed of the sound, plus the velocity of the listener, divided by V plus the velocity of the sound times the frequency of the source. The units of these things are going to be hertz because they're frequencies. Now note that V is the speed of sound and is always positive in our derivation. VL and VS are the respective x components of the velocity of the listener and the source. These can be either positive or negative depending on the direction of the motion of the source and listener. So to use this equation, you must define the positive x direction as pointing from the listener to the source. Okay, and this is our general equation, and that can work for a number of examples. Now, meteorologists also who study severe weather do use radar, and this really is using the Doppler effect because as things are moving, they're not stationary, and so there is a Doppler shift observed. So here is a tropical storm that's coming, and they're using Doppler radar to test this. And here's a Doppler radar shot from the College of DuPage weather lab also. So Doppler has meteorology applications as well as ultrasound applications. Let's test our understanding of this discussion. So with this problem, a police car siren emits a sound with a frequency of 500 hertz. As a listener, you are moving in the X direction also at 15 meters per second. So you hear the siren at a frequency of 500 hertz. What can you say about the motion of the police car? And this is multiple choice, and you should think about this. But the answer is there was no Doppler shift because you heard the same frequency that was there. And so there is not any relative velocity between you and the police car. So the answer is A, moving in the positive X direction at 15 meters per second. Police car is doing the same thing that you're doing because there was no Doppler shift. Now here's another example, and we should talk through this one. So a police siren emits a sine wave with a frequency f sub s. It is the source of 300 hertz. And on this cool day, and you see it depends on the temperature and everything else, but sound is moving at 340 meters per second. So A, we're to find the wavelength of the waves if the siren is at rest in the air. So, and then in part B, if the siren is moving with a velocity of 30 meters per second, find the wavelength of the waves ahead and behind the source. So here's the picture, and when the car is moving, it's there. It could also be stationary. So for part A, when the source is at rest, and we were supposed to find the differences between the wavelengths, we have from equation 1217, we have this. And from 1218, we have this. So we use those two. And so in front of the siren, we're using this one. We get the wavelength as this. And behind the siren, it is a longer wavelength. It is this. So we use this one here. We use this one here. Make sure you understand these examples. Here's another one. Now, a bystander observes the chase. Now, let's see what frequency a stationary listener will hear when the siren that we talked about in the previous example is moving away at 30 meters per second. So here you see the velocity of the listener is 0. They're not moving at all. And the siren, or the velocity of the source, is moving away at 30 meters per second. Well, we use the general equation in the master equation. So the frequency of the listener is this ratio times the frequency of the source. Now, V sub L is 0, so we put 0 there. And V sub S was 30 meters per second. And we substitute the 300 hertz frequency of the sound, and we get this as our answer. Now we're going to do something where both of them are moving. So suppose that the siren in the preceding two examples is at rest, and the listener is in a car moving away from the siren at 30 meters per second. What frequency does the listener now have? Now here, V sub S is equal to 0, but we're moving away this way. Again, we're using the master equation. So the frequency of the listener is, we substitute things in here, but notice this is minus 30 because we're moving away from the source. We substitute all those in. We have the velocity of the source is 0. Substitute everything in, and we get 270 hertz. Now, I guess we're talking about both things happening. So we're having the listener is moving at 15 meters per second, but the source, the police car, is moving at 45 meters per second. And that's what it's saying up here. Let's see. The siren is moving in the plus x direction with a speed of 45 meters per second relative to the air, and the listener is moving in the same direction with a speed of 15 relative to the air. What frequency does the listener hear? Well, again, F sub L is equal to this by equation 1219, which will be in your grace notes. And that's equal to, and you see they're both moving in the same direction, so they're both positive. And so you get 277 hertz when you do this calculation. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.